Thanks, Andrew. So thank you very much, Sudeshna, for agreeing to do this seminar today. Sudeshna is from Bangalore in India. Well, she did a PhD in Bangalore in India with Professor Vidya Hiraja and the late Mark Jarrell from Louisiana State. And afterwards, she went to Shanghai for about a
For
year.
about
Was
2
that
years.
right?
2
Or
years.
2 years? 2 years. And now she's back. Now she's in Dublin with Andrew Mitchell's group. So Sudeshna, we've been trying to arrange this for a while, as I mentioned. So unfortunately, now I have to do it online. So I really appreciate, Sudeshna, that you agreed to do this. And I guess I'll just leave it up to Sudeshna then to take it away. Thank you.
Okay, thank you, Graham. So I just need some time maybe to set this up. I mean, so I do share, and then.
Just to interrupt, I'm going to mute everyone but you, and if people want to ask questions, they can raise their hands. Right, just to keep random noises down. Okay.
Okay. Can you unmute yourself, Sudeshna? Just yeah, sorry.
I have unmuted her. So
First, okay, yeah. So can you see my slides now?
Yeah.
Yes.
I want to do full screen. I'm sorry for this. Okay. Not being able to do it full screen. But is this fine?
Yeah, it looks fine, Sudeshna.
Thanks again, Graham, for inviting me to give this online seminar. This is also a new experience for me. This is the first time I'm giving an online seminar. But let's begin with. So the focus of today's talk is molecular junctions, and a specific kind of set of molecular junctions where there are strong correlations in these molecular junctions. And then I also look into the interplay of molecular symmetry, the underlying molecular symmetry and strong correlations in these junctions. So at the outset, let me first acknowledge my funding agency, which is the Irish Research Council, and UCD Physics Department for hosting me, Andrew and my group here in Dublin for providing such a cool environment to work in. So let me just begin my talk. So I'm going to talk about low dimensional systems, as I said. So these molecular junctions, they fall into this category of low dimensional systems. And it's a confined space where in the confined space, you put in a lot of electrons, a certain number of electrons, and hence you expect strong interactions and strong correlations among these electrons and scattering happening in these systems. These pose enormous experimental challenges because designing such systems is very difficult. And at the same time, these pose enormous theoretical challenges as well. And at first go, you might think that, okay, these are low dimensional systems. We can always simulate it as a finite dimensional system with finite number of electrons. And then just, exactly find out the wave functions and things like that. But that's not the case, because as soon as you look at one of these molecules or these kind of systems, quantum dots for example, and then attach leads to it, then as soon as you do that, you are involving 10 to the power 23 number of electrons that can hop on or hop off from the leads. And at that moment, this becomes a many body problem. So it's not just solving this isolated system. It's really this leads the entire closed system. So conventional approaches, bottom-up approaches like density functional theory-based methods, which are first principles-based approaches, will not work in this case, and one has to resort to methods which are beyond these density functional based approaches. Or so accordingly you have to develop methodologies. And at the same time, there are these the quantum nature of correlations is very important, and these phenomena do not have any classical analog. So our strategy, as you will see, would be to develop methodologies such that we can derive effective models with proper information embedded in these systems in my effective Hamiltonian. So what do you expect then from this talk? So the brief outline would be, I would first introduce you to interaction effects, or how do interaction play its role in single molecule junctions. And then I would introduce you to molecular symmetries and how that can play its role or interplay with these interaction effects and lead to robust experimental signatures. But in this process, I will show you that in order to do that, we have to develop a unified theoretical framework that takes care of both interactions and molecular symmetries. So, so the idea then is to model a single molecule junction. So that's the aim. The aim is modeling single molecule junctions. And we as physicists, we always try to do this. I mean, we are all aware of this famous cartoon where we try to ignore all the details and then, you know, do drastic approximations, which work in most cases. In this case, we will do something similar, of course, but we just have to keep in mind that we have to have certain details, details and information, analogous information embedded in these effective models. So we have to take care of the structural details or the complex orbital structure of these molecules. The underlying molecular symmetry has to have, that information has to go in, and at the same time strong electron correlations. And there can be three approaches by which we can derive these effective Hamiltonians that would capture this physics, where approach one would be mostly what I will talk about in this seminar. That's semi-analytical and approximate approaches, which would be valid only in certain regimes. Approach two would be brute force numerics, but this is not always possible. It is difficult, but with state-of-the-art methods, it is possible in certain cases. And I will show you one result where we have done that using numerical renormalization group. That's a preliminary result, and it does not span the entire parameter space yet. And a third approach that is also being pursued in our group by Jonas and Andrew is machine learning based approaches, with the aim that over time we would be able to look into much larger systems and make more general predictions over the entire parameter space. Now, before I go into the theoretical technical details, just to give you an idea as to how relevant are these systems in experimental scenarios, or do we really see them in tabletop experiments and things like that. So it is indeed, and there are many studies on, for example, benzene based single molecule junctions. Benzene apparently is the minimal non-trivial molecular building block that shows such kind of exotic physics, interaction mediated physics in these kind of systems. And as you can see in this slide, I'll not go through, go read them off, but there are indeed several experiments that have been done. So it's not really just a theory, it is motivated by these experiments. Okay, so so the thing is, this is the first ingredient in these junctions, which is interactions. Interactions, if I want to put it in one word or just a phrase, I would say it is an interplay of competing energy scales. So which would be given by this relation. So for each energy scale, there would be a time scale associated. And if my quantum Heisenberg's uncertainty principle allows it, it will happen in these systems. And in these kind of systems, we have this propagator that carries information about all these underlying interactions and scattering due to electron-electron interactions. Now, in our cases, we will talk about a specific kind of, or a specific phenomena that is mediated by interactions in these systems. And that's like the spin half Kondo effect. So, so I'll spend some time on this slide. So to begin with, it has a history. So Kondo effect was not observed in the first go in molecular junctions. It was actually first observed long ago in a normal metal which had magnetic impurities in it. And what was observed that the conductance as a function of temperature below a certain temperature scale, normally we would expect that in a metal the conductance would saturate. But in those metals where they had this dilute amount of magnetic impurities in it, the conductance actually did not saturate, but it underwent a minima. So this was what first observed. And then Kondo came up with a theory, and later Anderson provided a model and a beautiful theory as to why this is happening. So the idea is, below a certain temperature scale, the conduction electrons, they coherently talk to this magnetic impurities, or the moment present on the magnetic impurities, and they coherently screen the moment. And this, in normal metals, this acts like a scatterer. And that scatterer beyond a certain temperature, because this or below a certain temperature, this because this scatterer has formed, so this scatters, this increases the scattering cross section, and that reduces the conductance. And beyond that temperature, they just randomly scatter off, and there's no coherent screening happening. So this is known as Kondo screening that happens in a normal metal. Now, in these junctions, what happens is we have two leads. So let's call this source and this as the drain. And here again, you can imagine that you have one magnetic impurity, say a moment, with a spin, a residual spin sitting here. But then because of this U, because it's interacting, I cannot just put an electron here. If I put an electron here at this level, another electron, firstly, it has to be of the opposite spin, and it has to pay an energy cost U. So it will not remain in this state, but it will go in this state. However, if this is allowed, if this is satisfied, in other words, imagine I have this level sitting here, and if I just look at it classically, then an electron cannot just go from the source to the drain, because this is classically forbidden. However, quantum mechanically, this is allowed, and provided that the time spent on this virtual state follows this relation. So indeed, that is observed, and this is called coherent tunneling. So this is not the normal sequential tunneling happening. This is coherent tunneling that can happen. And in this process, what can happen is, given the time scale or and the energy scale associated with this level, an electron in the process of going from the source to the drain would in between flip the spin, or even this electron would, when it goes from here to here, it could flip its own spin. So this is spin flip scattering that is happening in this system. So that's basically Kondo effect. And this can happen in an off resonance situation. This will not change the ground state of this. So even at zero bias, you should expect some low conductance in your experiments. And that's exactly what happens in these coherent co-tunneling, Kondo-mediated co-tunneling processes. So this transport from the source to the drain is happening via these high energy virtual processes, which are allowed by this relation. But since uh, it's contributing to a current, you see the conductance increasing, and at zero temperature, we actually should see this unitarity limit. So this, when you see in the experiments, this is actually the Kondo enhanced conductance. So this is observed in these kind of systems. That's basically the Kondo effect that is happening in these systems. Now, in our case, of course, when we look at complicated molecules, it's not just one level sitting here. So it's not just this. It's actually several levels here. And it's also the energy gap between these levels. That is one thing. And the second thing is, these levels could be degenerate or non-degenerate. So all these things have to be taken care of when we are looking into, when we are trying to generalize this whole scheme. But the main idea is that our generalized scheme would involve projecting out all these high energy charge fluctuations. And when you project them out, all these high energy charge fluctuations, the basic idea is that you do not change the ground state. So the electrons are hopping from the source to the drain via these tunneling processes, but you have kept the number of electrons and its ground state the same. Now, as I said in the previous slide, that about the spin half Kondo effect. So my focus today would be to project out onto a subspace that has an effective odd integer charge state, so that in the end you are left with an unpaired electron in one of these levels. So I have an odd number electrons, and I can expect a doublet ground state which has this one unpaired electron. And that in itself, that in effect, in essence, would give an effective spin half system and an effective spin half Kondo effect. And there are real molecular systems where you can end up with odd number of electrons, ground states with odd number of electrons. So you can end up with doublet ground states. So let's see what happens when we try to design this in this more generalized context for a non-degenerate ground state. So, so what we have now is, so the talk will become a little bit technical from now on. So now we have a Hamiltonian. So the Hamiltonian has three parts. It has the leads, it has the molecule, and it has the hybridization that tunnel couples the leads with the molecule. So this tunnel coupling is given by these amplitudes V's sitting here. The alphas would label the leads. And these are the molecular degrees of freedom. Now let's just go through the molecular Hamiltonian. So let's imagine it's a finite system with a finite number of sites. So I and J runs, say, from 1 to certain number of sites. There is a hopping, all kinds of hopping can be present. And there is a U, and there is also another density interaction, which is beyond the on-site level. So this is, I mean, chemists call this this Paris-Poppel Hamiltonian. Now what we are saying is that we won't allow the charge state to change, which means what? We can do a perturbation theory in the H hybridization. And that would help us project onto an n electron ground state. And if we do that, if we just do that perturbation theory to second order, then we would end up with an effective Hamiltonian, which would have all these these effects of these hybridization coupling. And so we have essentially projected out on an electron ground set. So essentially we have just kept some n electrons and a spin half here. So that's my S molecule. That's a spin half. And these effects of hybridization, including the interaction here, is all coupled with these co-tunneling amplitudes, or these exchange, these exchange coefficients J's, that couples with these conduction electron degrees of freedom that basically screens this molecule, this effective spin half sitting over here. And accordingly, you will end up with some potential scattering terms, and of course the H leads. But for us, the main, so these will just shift the energy level. So the main dynamics, the interaction effects are coming from these H exchange. And that's
so
the general, yeah.
Sorry, can I interrupt? Just to understand which each of the operators are, can you say what the D's, you have? Yes. D's and C's, is that?
Yes. So, so the D's are the molecular degrees of freedom. Okay.
And the C's are the electron degrees of freedom.
Yeah. So that's hidden here in the S mole. So after this, this projection onto an n electron ground state, that's hidden here in the S mole. And the C's are the conduction electrons.
Okay, thank you.
Yeah, so so effectively we can see that this is like a spin-spin scattering, which shows in this schematic. And the sign of J, by the way, is very important, which I did not mention. For Kondo effect to occur, this sign of J has to be antiferromagnetic. So this interaction has to be antiferromagnetic. Only then it can flow to that Kondo fixed point in the RG sense. So that's also important. So the point is that traditionally we would just look at a single site system over here, but here we have the most general scenario where you have a finite sized cluster, but then you treat the hybridization in a perturbative fashion to boil down to, you project out all charge fluctuations to boil down to an exchange Hamiltonian, where effectively you have a spin half sitting on your molecule and you have these Kondo interactions. But these J's here would have to be determined now, and that's what I'll show you in the next slide. And the sign of J's is also important. Okay, so so in the previous slide we had projected out, and this was, so for that, the first thing that we need to perform that projection is to build a projection operator. So we want to project onto an n electron state. So the wave functions corresponding to that n electron ground state would be involved in projecting out onto that state. And these can be obtained by solving the isolated molecule Hamiltonian. So we can just take the cluster and exact diagonalize it. And then we basically perform this. Then we end up with this. So so actually this is what we end up with. And in the previous slide, this was recast into that Kondo-like term, into that Kondo form, into that generalized Kondo form. So this is my exchange Hamiltonian, actually what I get from here. So let me just go through it. So I have the conduction electrons here, sitting here, which are tunnel coupled to the molecule. And this actually is contributing. So these will contribute to the construction of that S molecule, that effective S molecule that I have, the spin on the molecule. And these look like this. So these are the co-tunneling amplitudes that get involved in giving you the J parameters. So basically the exchange couplings. Now, so what are these co-tunneling amplitudes telling you? So it looks complicated here, but if you just go through, if you just look at it in a bit deeper, you would just realize that what this is doing is it's producing those virtual charge fluctuations. So from the n electron, this is going to the n minus 1. So similarly, this is like creating a whole like virtual state, and this is like creating a particle like virtual state. So this is the exchange co-tunneling amplitude that in the end results, I mean, via these relations, we can show that this is actually creating a J. But this J now is a matrix because I have two leads. So in general, I can have a screening only between the left lead electrons and the local moment sitting here, or I can have screening between the right electrons screening this, or there could be these correlated tunneling processes where a spin flip can occur from here to here via these JLR kind of exchange correlations. So this is in essence what we will get by doing this projection. And the main idea is to derive the J's. So the thing is, we start from a most general most general Hamiltonian for the impurity for the molecular cluster. We solve it and we get the J's. So we get a Kondo-like, generalized Kondo-like Hamiltonian. Now, what are just a little bit more on this? These co-tunneling amplitudes sitting here. So what are these terms actually? Yes, they are leading to these virtual high energy processes, but this is also giving you these quantum interference terms. Because if you look at these terms here, these are actually, so the molecules have these frontier orbitals sitting. So these induce that kind of interference between these wave functions, between the left and the right. For example, when alpha and alpha prime are different, that's actually the quantum interference terms. And yeah, so basically these are the ones that lead to the quantum interference, and these also are the ones that mixes the left and right leads. This happens for a non-degenerate ground state. So what could happen? So let's now take an example which was done in 2017 on several sets of molecules. And what was observed that there were these quantum interference nodes purely because of these strong correlations. Because remember, the J terms, the terms that mix the leads lead to conductance, and the J terms are there because you have done this kind of projection. So effectively, if you do not have interactions, you would not have these effects at all. Now, what that does is that as you change temperature, you can see that as we change temperature and we tune the gate voltage, so such that we are still at in the n electron ground state, but we can tune the gate voltage to tune the chemical potential, and we would see that the conductance starts from the unitarity limit where it's Kondo enhanced, but then it goes down to 0 at certain gate voltage. So the zero bias conductance goes down to 0, which means there is a blockade of conductance, and that's what they call Kondo blockade. And that manifests in the, if I just plot the zero bias conductance as a function of that gate voltage that tunes the denominator in my quantum interference term, then uh, that appears as nodes in my conductance pattern. So that's the fingerprint of a quantum interference node that is purely happening because of the Kondo correlations. Now we ask the question, what happens if I attach the leads in a different position? So I have so the question then boils down to what is the role of these frontier orbitals, or what happens if I change the symmetry? So this basically determines the overall symmetry of the system. So that's the question that we'll look into. Uh, so the question is the role of molecular symmetries, and indeed there have been experiments where they have seen different quantum interference patterns depending on where you attach the leads. For example, in this figure, this setup, this configuration gives a different quantum interference pattern than this one. Now in experiments, of course, it's in these experiments it was not mentioned whether they relate to, or that was not the focus, whether they are relating to how the Kondo effect is also leading to those nodes. That was not the focus there. But the bottom line is, depending on the configuration, which means depending on the symmetry, your quantum interference nodes will change. And that's basically what I'm going to talk about in this later part. So the idea is different positions of leads means different overall symmetry. So somehow that information has to go in if we want to understand the role of molecular symmetries and strong interactions. Okay, so symmetry is beautiful. So I just want to share a short story, which is recently when I went to India and I visited Taj Mahal, the first thing that I noticed was this beautiful symmetry. I mean, it has this beautiful bilateral symmetry, and you cannot help but notice it. And as trained physicists, we have to notice it. Similarly, if you look at a beautiful butterfly, this happens. But in real, for us, like solid state or chemists, like these molecules, symmetry we know plays a different role. For example, IR spectrum, vibrational spectrum, these are all determined by the symmetry. And similarly, solid state, all our systems are classified according to that. And of course, I have not listed out any mathematical symmetry that also determine several other physics, exotic physics. So symmetry is beautiful. And let's see what happens. Just a basic thing. There are several kinds of symmetry. What I will be focusing on is mostly is geometrical symmetry. So the underlying structural symmetry has an effect. And also, because I'm dealing with interactions and fermions, I have to take care of the exchange of particles and the antisymmetry associated with that. So these are the two basic symmetries that I have to take care of. And we know that various consequences of symmetries is various conservation laws. Particularly in my case, which would be apparently visible, is the characteristic transformation of these Hamiltonian eigenfunctions, which would be very important. And symmetry, we know, is the root of degeneracy. Until now, we were looking at what would happen if we had non-degenerate ground states. And we have to embed this information in the construction of this entire formalism. So basically, what from now on I'll show you is how in order to understand these systems, I'm constructing these symmetry-adapted many-body eigenstates and embedding that into the formalism. So just going back to the slides on the non-degenerate ground states, if in essence everything follows, but it's just that these quantum interference terms will now have more labels, because we have degenerate ground states. And how to label them, there comes the role of symmetries. But before I go to that, let's see how these co-tunneling amplitude terms would look like if I have degenerate ground states. So let's say I have a twofold ground state. I'm not considering the spins. If we're just considering the spins, then it's fourfold. And let's say I name them as plus and minus. So each of them will have plus, sigma, minus, sigma labeling. The first step would be to construct the projection operator. And the projection operator would now be a sum over these states as well. It's as simple as that. And then I follow the same procedure. And then I get the exchange. I project out the charge fluctuations. And I get an H exchange. And the H exchange has all these terms. So basically, I have these 4 states sitting over here. So now the J matrices, so this is what determines the J matrices, and that has these additional labels for these degenerate quantum states. So now I come to the question as to where would we see it? Of course, we would see it in systems where there is a lot of symmetry, and hence your ground state itself is degenerate. So now I explain the algorithm with which I will calculate, with which I will derive that whole setup again, or evaluate that whole setup and calculate the J coefficients. So let us take an example of a triangular setup. So let's imagine, I mean, we can also get triangular molecules, but let's say it's a toy model, or we have a triple quantum dot setup. Which has been seen in experiments. So let's say we have this kind of a setup and we attach these leads. Now this system, if I attach the leads, then has this overall, I think it reduces to C2V symmetry. But if I just look at the isolated molecule alone, then I have this C3V system symmetry. And we know that from group theory, the maximum allowed degeneracy is 2. So we can construct irreducible representations which are 2 by 2 in dimension. Now, the first step is I have to construct. So the first step is I write down the molecular Hamiltonian, and then I construct each of these symmetry operators, all these symmetry operators, you in the Fock space basis of this H mole, or of this system rather. So one can go on and just keeping in mind about fermions and what happens. So keeping in mind about a particular order, the conventional way in which we construct fermionic basis functions, we do that, and we construct this kind of an operator representation for each of these C3V symmetry operators. So that's the first step. Now the second step would be to construct a matrix representation of these symmetry elements in that basis. So that's denoted by this bold P. So for each of these okay, so the first thing is we choose in the previous step, I forgot to mention. So the first step was to choose the particular symmetry operation that is relevant for us, and which was in this case this mirror symmetry, because that respects the overall left-right symmetry. So out of all these C3V operations, symmetry operator elements, I choose that particular symmetry operator, and I create and I construct its matrix representation in the Fock space basis for this toy model. Remember, it's an interacting system, so it's not and I have a certain number of electrons, so it's not just 3 by 3. I mean, I'll have several states. So anyway, so I have all these Fock space bases, and I have a matrix for that. Then I diagonalize that particular symmetry element, and then I construct this block diagonalized form of H mole. So basically I write down my Hamiltonian in the eigenstate basis of these P matrix operators. So once I do that, I have actually labeled my Hamiltonian eigenstates in terms of the spin quantum number and the eigenstates of sigma v1. So that's the basic essence. So once I have done that, I have put in the information about the underlying symmetry into my Hamiltonian eigenstates. And then using those states, I calculate the co-tunneling amplitude. Now, is this all? Actually, it is not. There's still a catch. So the catch comes from the following problem. So for this, I go back to this expression here. So remember, I have to calculate these kind of observables, I would say, where I have these different states, and these states are labeled by the particular symmetry operator that I have chosen. But in my calculation, I have what I have done until now is I have imagined that since I have block diagonalized it, I can just individually take this block, diagonalize, individually take this other block and diagonalize. If I do that, I might end up with a phase ambiguity associated with the numerical diagonalization, and that phase ambiguity has to be removed. And in fact, that phase ambiguity cannot be there because this is an observable. So this is like a paradox situation, but this can be actually fixed by group projection. And for that, we have to utilize all these other symmetry elements, and then just perform the group projection, standard group projection technique, to go from this basis vector space to this space. So that's what we have to do. And then once we do that, we can uniquely fix the phase, and then this phase ambiguity goes away. And why we can do that is again rooted to group theory, because we know that these are degenerate eigenstates. They will form these two-dimensional representations. So we can use all these group theoretical and symmetry information to uniquely diagonalize and obtain the ground states that are required for calculating my J coefficients. So just to summarize the algorithm, I begin with a molecule. I have these tunnel coupling. I project out charge fluctuations, and I end up with a generalized Kondo-like model, where these J's can be matrices depending on the number of degenerate states here and the number of leads here. Okay. But in order to do that separately, I have to look at this cluster here. I have to exactly diagonalize it, and to have all the correct information of the underlying symmetry, the allowed symmetries, and the allowed way in which the eigenfunction should look like, I have to symmetry adapt them. And for that, I have to choose the particular symmetry operator that respects this overall symmetry. And once I do all these things, I will uniquely determine J matrix by the knowledge of the molecular symmetry and interactions. So that's the summary of the algorithm. So let's now just go to, so towards the end now, I just demonstrate an example where there are more than these kind of symmetries. In a triangular system that I had shown, there was only one mirror plane over there that respected this overall left-right symmetry when you attach the leads. But when you have a benzene-like system, which is like a hexagon, if you want to think in that way, then we have more such attachments possible. And so in the beginning, I had one slide as to where I asked the question, what happens if I attach the leads in different positions? So again, if I just blindly solve it, I know that I will get symmetry in itself determines that I will get a degenerate ground state here. So I choose a sector, which would be 7 electrons, so that I end up with one unpaired electron. So I know that I will end up with a doublet ground state. So this is the ground state or the regime where I will look at. Now I again construct the projection operator, but let's say I first do this parity symmetry operator. I call this parity symmetry, where I have this mirror plane over here. So I do all those things and I label them as the eigenstates as plus or minus one, depending on the eigenvalue. And then I end up with this complicated exchange Hamiltonian with lots of labels. But now the question is, can this be recast into a different form? So what are these degenerate levels actually? So if you recast it, we can actually write it down in a form that involves these pseudo spin like terms. So these parity states are actually looking like they are pseudo spins. So there is the S molecule, which involves the actual spin, and then there are these plus and minus states which look like a pseudo spin, and that also gets involved, and you can have a kind of a pseudo magnetic field. Now this is right now a bit incomplete because we have not really cast all our these bare J's in terms of these K's and the T's. But in essence, you should end up with this, where you have a spin and a pseudo spin, and there are like you have these spin flip, original spin flip terms, you can also have these pseudo spin flip terms, which would be encoded here. Right now, for today, I would leave this recasting at this position just here, because we have not gone into the details of it, but we should be able to do that. But let's now go to a slide where I now derive these J matrices and I derive the quantum interference patterns. So first I show for a 1,4 benzene junction. So basically this is the overall left-right symmetry. Now I have several J's, right? So I have the plus and minus states. So each of those plus spin on the plus states, an overall spin on the plus states can get screened by the left electrodes or the right electrodes, and then there can be these LR mixing term. There can be the LR, the plus minus spin flip exchange terms, and all these things can be present. So in this symmetry, what happens is, of course, there is pseudospin selective quantum interference node. So let's just look at the ones where there are no pseudo spin flips. So there only one of the pseudo spin displays a quantum interference node. The other doesn't, as a function of the gate voltage. And so that's why I call this symmetry forbidding certain Kondo mediated co-tunneling events. So at certain gate voltage, those co-tunneling events are blocked. But another interesting point is that these kind of terms are completely absent in this geometry. So this is also so this is what I call a lack of pseudo spin flip. So this quantum interference pattern signature has all these signatures in fingerprints in there, which are because of this symmetry over here. Now we change it and we attach the leads at a different position. So now my symmetry, so this I call 1, 3. So this is 1 and this is 3 where the leads are attached. So now I have the mirror plane sitting over here, and as you can see, it's a very different quantum interference pattern, in the sense several of the J coefficients display these nodes over here except one. And while in the other case, these spin flip terms were completely absent, here we have the spin flip terms. So depending on the symmetry, my quantum interference pattern, which is Kondo mediated quantum interference pattern. So the Kondo blockage structure will also change. And of course, I've not shown all these things, but they are all related by the underlying symmetry. So the main essence here in the 1,3 junction is that pseudo spin flip terms are present, and it's distinctly different from the 1,4 junction. So the role of symmetries is, what is happening in the 1,4 junction is that the overall symmetry group is D2H, whereas in the 1,3 it's different. And here I do not have the spin flip terms at all. Here I do have the spin flip terms. The signs are important. Now, why this is happening is because the ground parity eigenstates are different. So that information in construction of the Hamiltonian eigenstates, the ground states have changed, which means that the effective model, which we did not analyze, but which we presume would obviously be the effective model, that would definitely change. And this would affect the quantum transport, where I would not, I just have one data for that, so I'll show that. And secondly, the sign of J's are also important, because depending on the signs, we can either have an antiferromagnetic or a ferromagnetic kind of Kondo effect. And yeah, so the idea is that where the frontier orbitals are situated determines my quantum interference nodes, and that in essence determines the effective model. So the symmetry is playing an important role in determining the underlying effective interacting model actually. Now, just one slide on some calculations as to what the physics could look like. I mean, we have not derived this is not complete in the sense that I had displayed the effective model in one of the slides, but we have not connected it with the bare J's that we derived. But let's say we just brute force do a numerical calculation on this system in this configuration where I have attached the leads as at 1 and 4. So what we see is, and then we can just plot, first we plot the entropy here as a function of temperature. We see that, so in the beginning, we have both the spins at high temperature, the free spin and the pseudo spin. They're not talking to the Kondo, to the conduction electrons yet. But then as you reduce the temperature, these so here I have both these spins getting I mean, they are showing there. So here this is something random where everyone is talking to each other actually, but here you have reduced the system to a scenario where you have a free spin and a pseudo spin. So you have this entropy here contributed from both these. Then you reduce the temperature further, you see that one of the spin just freezes, it just freezes out, and you're left out with this one free spin, and in the end eventually that gets Kondo screened over here at very low temperatures. So eventually if I look at the conductance, then I would end up with a Kondo enhanced conductance due to this eventual screening of this free spin. But in between, all these interesting physics happens, and this is just at one such gate voltage. This is not even at the quantum interference node, at the gate voltage where I can experience a quantum interference node. So this is what happens when I have the 1,4 configuration. It would be interesting to see what would happen if I am at the 1,3 configuration, and of course at a quantum interference node. So that's the final result that I wanted to show. So to summarize, so what I've shown is that the molecular symmetry and the frontier orbitals that connect to the leads determine the effective Kondo exchange terms, and hence that will determine the effective generalized Kondo model. So we started from the bare minimum model that has all these information embedded, and we developed a formalism where we utilize the symmetry-adapted basis functions. So my ground states do know about all these information, and that leads to very distinct fingerprints on the symmetry fingerprints on the quantum interference patterns. And of course, in the last slide, I had shown how emergent physics happens. For example, the pseudospin freezes out, and what is the effective Kondo screen molecular state? We have not defined that, but this is not just one lead screening one local moment. So it's something effective. We have not figured that out, but that is what is happening. And these will manifest as robust and unconventional experimental signatures. So that's the take home message here. As an outlook, I believe this methodology could be generalized, is generalizable for more complex structures that includes several other, multiple molecular orbitals, for example, and then magnetic and other parameters involved for other experimental scenarios. For example, if I have a magnetic field, what happens to these nodes, and what happens to the effective model. And of course, one can embed this with methods beyond exact diagonalization. For example, if I want to explore larger molecules, I'm limited to a certain size of system here because it's an interacting molecular cluster. So that's also as an outlook that should be done. And of course, these are all spin half Kondo systems. So what happens if I explore high spin systems? For example, I project out onto a spin 1 or a higher system, which is also very experimentally relevant. In that case, we should expect some underscreening or overscreening stuff. So that's also remains as an outlook, and that should be done. So with this, I thank you for attending, and thank you for listening to my talk today. Thanks.
Thank you very much, Sadeshna.
Questions? Go ahead. I'll leave it to you.
Okay, yeah, thanks, Sanjay. Anyone got any questions? I'm not sure I can.
I have a question.
Sure, Pavel.
Well, I was wondering that you were talking about these properties of the symmetry, how this exchange coefficient J change when you change the symmetry of the molecule, or the molecule junction. Yes. So the question is, this has some influence in the conductance behavior of the conductance. I mean, if you change the symmetry, I mean, you will change the J, and then maybe you can expect that the conductance somehow will change or not.
Yes. You mean quantum, did I hear it correctly? You mean quantum transport, you said, is it?
The conductance that you plot at the end.
Yeah, of course. I mean, this way, for example, if you can clearly see that for this 1,4 junction, I have this quantum interference node. Now, exactly for this junction, we had like numerically done this calculation, but at zero temperature it shows Kondo enhanced conductance. I believe that if I just look at one of the I believe that if I look at one of these nodes, at this node, one of the pseudospins completely decouple, but there are these other pseudospins present as well. It's not a priori clear to me what the effective Kondo Hamiltonian would look like. If it's just like a normal Kondo Hamiltonian, then we would get I mean, this kind of a pattern always in the conductance. For example, I would have a Kondo enhanced conductance, and then I would have this. But if imagine all of these J's, if imagine all of these, so basically this is also one more thing. This is taking you from the left to the right, right? So here in the conductance, the J's that get involved are the JLRs.
Okay.
Right? So what happens? So to understand what would be the effect of quantum interference nodes on the conductance, we should really focus on the pattern of JLR. Now in the 1,3 junction, I can clearly see that the JLR has a node here for one of so for this pseudo spin flip term, and then there are nodes here as well. So yeah, I mean, it's not a priori clear, but JLR terms are the ones that will influence the conductance. And that will also determine whether I have, what kind of Kondo model I end up with. So yeah, it's not straightforward to see unless we do all the calculations by heart, but yes, it's the JLR that will determine, and the JLR is also influenced by the symmetry.
Thank you.
Anyone else any questions? I wanted to ask briefly, Sudeshna, about the method itself is based on perturbative study, and basically I'm wondering, what is this small parameter? It's the lead coupling here, right? Or
yeah, so first of all, it's not perturbative in U. So U is treated in a very state-of-the-art way. But yeah, it's perturbative in the hybrid molecule lead coupling. And it's small compared to the charging energy. So, I cannot allow for the ground state to change. So
sure.
or in other words, yeah, I mean, so I say I have a ground state. So my n electron state is a ground state, right? And I have a charging energy which will take me to another electron sector, say an n+1 sector. I cannot allow that to be the ground state. So yeah, there's a subtle
Yeah.
thing
And
on
then
that. So it has to be less than that.
okay. And so, I mean, let's say you consider then, so you kind of cut off at second order.
Yeah.
I mean, what other type of kind of effects could you get if you allow for higher orders?
Higher orders would higher order is difficult in the sense it would yeah. So you see here the Q over here. The Q is actually all those charge fluctuations into n+1 and n-1, but it's like two hops in Q. So for higher order, even so, this Q matrix is actually still the it's like still the bare Hamiltonian term for the n+1 and n-1. I have to really see, I mean, this in itself will change. This ENs in itself will change. So in terms of processes, of course, this would mean that it's not just one hop. It's not just two hops that the the lead electron goes from the lead to the impurity to the other lead. It's not just two hops, but it's more than one hop in that sense. Yeah, it's not trivial.
Okay.
So if I can ask a question, so you obtain these psi functions as eigenfunctions of the isolated molecule, is that right? So
exactly, yes.
So you know the structure of the molecule itself well enough to compute those in some way?
Yes.
And then you say that you have different possible charges on it. So, but the number of electrons surely on the molecule when it's isolated is fixed. So how do you add then electrons on
Yeah,
it?
so no, that is fixed. So when I solve the entire system is, you can say in that sense that I have an n electron system here. So at a time, the ground state is always of that of an electron for the molecule. All these n+1 or n-1 charge states, these are not really the charge states of that cluster molecule. These are like just like virtual processes that is happening. So when I solve it for n electron, and all those virtual processes are embedded through this hybridization here.
Yeah, but I don't understand. So how you solve it for n?
Okay, oh, I see. What you are asking is here, when I'm trying to derive this, do I also need to solve these psi n's and all? Is that the question?
Yes.
Yes, okay. So I also have to do a calc. Yes, you're right. I have to find out the entire spectrum for n-1 and n+1 as well. Yes, for the isolated system. Yes, I need that.
And then in your final results, you have the J, but it seems to be positive. And you said it was necessary for the Kondo effect to be negative.
Yeah, okay. That is a bit misleading because I did not show the original J's. I did not discuss the sign of J's. Yes, that is true. But here the idea was just to show you that there could be these quantum interference nodes. Okay. For your information, these J's were indeed positive. So these were actually antiferromagnetic coupling. So here I wanted to show, so if I had just shown the, with the sign, then I would have this crossing at 0. Yeah.
Okay.
Does that answer the question?
Yes, I guess so.
Sorry, anybody else got any questions? Well, if not, then I guess we'll just thank Sudeshna again.
Thank you.
Thank you.
Thank you very much, Sudeshna.
Yeah, thank you very much for attending the talk.
Yeah, it's great. It was really nice. I think you realize that we're not all condensed matter physicists, and a nice friendly introduction to the topic. We appreciate it.
Yeah, this was my first online seminar, and I'm happy. So I presume this is recorded. So how do I get the link? Then would you like send it to me?
Yes, it should be available on our webpage. You will have, and if you can send us your transparencies, I'm going to stop recording at this point. This is not necessary.